Okay, so we're going to work this test here today, and not really a whole lot to say about that. So we'll start by, I really hate writing key. It really makes things makes things a little stressful, as if everything's going to be exactly perfect. So let's start with the true false. The first one, streak lines show the path of individual particles in a flow. That should be a path lines if it was true. Okay, so this is going to be false. Second one, the pressure head plus the elevation is called the piezometric head. So this is P on gamma plus Z. That is the piezometric head. Okay, that's just a definition. Basically, it's the potential energy. Okay, the Reynolds numbers tend to decrease with more viscous fluids. So the Reynolds number is Vd on nu. So if the denominator increases, then the whole quantity is going to decrease. So this is true. The time rate of change of velocity is called the convective acceleration. So that basically means, usually you've got du dt plus u du dx plus v du dy plus w du dz. And this right here is the local acceleration. And this is the convective. Okay, so the time rate of change of velocity is this guy right here. And so that is normally it's called the local acceleration. It's never called the convective acceleration. This is the convective over here. Okay, convective is the spatial accelerations. A tidal flow near a river's mouth would be considered unsteady. And as one of you pointed out, it would obviously depend on the time scale of the question. But if I'm mentioning that it's tidal, my point here is to kind of get you to think about the unsteadiness, okay, the fact that the tides come in and out and that sort of thing. If I just said, flow near a river's mouth would be considered unsteady, well, I don't think you'd even be able to answer that because that totally depends on the time scale. Obviously, tidal flow does too, but if I'm mentioning tidal, I'm trying to drive that. Like, is it changing? Well, tides change in time fundamentally. Okay, an object submerged in mercury will have the same buoyant force acting on it when it's submerged in water. The buoyant force equals gamma the fluid times the volume displaced. Okay, so if you change the fluid, you change the gamma of the fluid, and so that's going to change the buoyant force. So this is a false. The Bernoulli equation assumes that the fluid is incompressible. It does do that. Okay, there were 4 assumptions for the Bernoulli equation. I don't know if I can name them all off the top of my head, but along a streamline, incompressible, steady, and inviscid, so no viscosity. Okay, turbulent flow in pipes tends to have more uniform mean velocity profile than laminar flow in pipes. This was the trickiest one. Okay, and I've drawn this one in numerous times, but the laminar profile looks like this. It's kind of like a parabola, so that's laminar. And then the turbulent one kind of looks more like, it's more like this. Okay, it's flatter. Okay, and so the turbulent one is in fact more uniform than the laminar flow in pipes. That was probably the trickiest one, and probably the one that got most people. And so this one, the mass flow rate of tank into a tank of constant volume is greater than mass flow rate out. So we've got 10 kilograms per second going into a tank. And we've got 5 kilograms per second coming out, let's just say. Well, then every second, we are accumulating mass in this volume that's not changing. So the density must go up. Okay, because, if the volume could expand, well, then the density wouldn't have to go up. It could stay the same. It could even go down if the volume were expanding fast enough. But in this case, the volume is constant, so it has to get more dense. Okay, and then the last one, the buoyant force on a submerged beach ball is the same as when the ball is inflated as when it's deflated. The buoyant force on a submerged beach ball is the same when the ball is inflated as when the ball is deflated. So that goes back to this equation right here, the volume displaced. If you increase the volume displaced, okay, you're going to increase the buoyant force. And anybody who's submerged a beach ball in a pool knows that when it's inflated, it has quite a buoyant force. Okay, so this one surprised me that we had some issues on this one. And I guess, we'll just do what we can do here. Let's see. Let's see what happens if I... Okay, so I decided to float down the Mississippi on a raft made of teak wood. There should be a drawing here, but I guess this version did not have the drawing. So I'm just going to go ahead and This is a very unusual thing. So here's my raft, and right at this point, okay, it's going to be right at the surface of the water when I load it up exactly. Okay, so there's me standing on it. I've got some supplies right here. I think we need a darker color here. Let's go here, and let's go back to that. Okay. All right, so we've got some supplies and we've got me. So the free body diagram, and I'm really confused why we had trouble with this one. Okay, a lot of you forgot the weight of the raft itself. So basically, if we do this free body diagram, we've got the weight of the raft. Okay, we've got the weight of, I don't know, me, and then we've got the weight of the supplies. Okay, and that's what the buoyant force has to hold up. So that's the force of the buoyancy. Okay, so that's your free body diagram. And if we do the sum of the forces in the z direction equals 0, then that means the force of buoyancy minus the weight of the raft minus the weight of the supplies minus the weight of me equals 0. Okay, and so I think that was just kind of getting that concept was worth a point. So the buoyant force is the gamma of the fluid. In this case, that's water. So we'll just go ahead and put a W there. Okay, times the volume of the raft minus the weight of the raft, which is the gamma of the raft, times the volume of the raft, minus the weight of the supplies, well, that's the mass of the supplies times gravity, minus the weight of me, well, that's the mass of me times gravity equals 0. Okay, so let's see, we'll go one more step, gamma of water. The volume of the raft is, this thickness of the boards. So maybe we'll call that lowercase t. Lowercase t times the area, the top area, okay, minus gamma raft times t times a, minus ms plus m. Okay, I'm just gonna make that algebraically like it's all one thing. And then we just gotta solve it, and we could combine the first two terms as well if we wanted to. I think that's how I did it in the key that I posted. So the gamma of water is well, that's kind of hard, right? Because they didn't give us gamma; they gave us rho. So we'll use rho. So we'll use gamma of water here. The gamma of water is 90. What units are we using here? Yeah, we're using so 9810 newtons per meter cubed. Okay, times the thickness, which we know to be 0.30 meters. Okay, times the area, minus the gamma of the raft. Now the gamma of the raft is 950 kilograms per cubic meter, times gravity, 9.81 meters per second squared. Okay, so that's gamma raft, that's gamma R. Okay, times the thickness, 0.30 meters. Times the area, okay, minus ms, the mass of the supplies is 10 kilograms, plus the mass of me is, I think I said 70 kilograms. I think that's about right. Times the gravity, which is 9.81 meters per second squared, equals 0. Okay? Make sure you note that this is just letting you know what this is. It's not a fraction. Okay? So if we solve for a here, we bring this over to the other side, divide everything, blah, 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 we'll get a. And the area ends up being 5.3333 square meters, which I will note that's 5.33 square meters. Okay, and so that's how you do the first one. All right, okay, so let's zoom out. We're not gonna do that one yet. We'll do number 3. Okay, consider the confluence of the Yellowstone, Missouri rivers as they flow downstream towards the Mississippi. Okay, so here, this is the yellow. This right here is the Missouri. Okay, and really, to make it simple, we wouldn't think about it that way. We would think of it this way. In case you didn't notice, by the way, to my mind, I kind of thought of this test as a river test. I wanted to do some rivers. It's what I study. So we could think about this as the yellow coming in. This is the Missouri coming in. And then 1 mile downstream somewhere, right there, there's the combined. Okay? And then there's another place where we have stuff coming or going. I don't really know. And I probably want to be consistent with my drawing here, but I'm going to assume that the groundwater is coming into this river. I don't know why. You could have chosen it another way. So what we need to do is we need to create a continuity, so a mass balance, accumulation. Okay, so what's going in? Well, rho times Q of the Yellowstone is going in. Okay, so that takes care of this arrow. Plus rho times Q Missouri, that's coming in. Okay, to our control volume. So here's our control volume, right? Then we got some groundwater. Rho times Q GW. Okay, so I'm assuming it's going in. So if I end up getting a negative number, that means it's going out. Okay, equals out. Well, what's going out is the combined flow. So rho Q combined. Okay, and then we've got an accumulation term here. And so the accumulation is going to be d by dt of rho times the volume. Okay, so the first thing we're going to do here, just because it's going to make our lives a little easy, is we note that all these rows are the same. This row gets pulled out and canceled. These rows all just get canceled. So now we've just got Q's, which we much prefer. Okay, because densities sometimes can end up being a little bit complicated. Okay, so QY, well, we have numbers for all of these. I'm going to do one intermediate step here so I can get this d by dt. Okay, I'm going to change that volume into the area times the height. So this is going to become h, and this is going to be the area. Okay, so that area being, if I were to draw on our picture here, it's the top here, right? Okay, and it's not exactly a rectangle, but we're basically assuming that it is, just because it's a good way to kind of get at an estimate of what's going on here. Okay, so now we can kind of plug in. Let's see here, QY plus QM plus QGW equals Q combined. Okay, so QY is 13,770 CFS plus QM, which is 4960 CFS, plus QGW, which is what we're looking for, equals the Q combined, 17,480 CFS, plus the area, which is going to be 5,280 feet, 1 mile, times 300 feet wide, times DHDT. So DHDT in this case is, it says it's rising at 1 foot per hour. So it's positive 1 foot per hour, 3,600 seconds. Okay, so if we rearrange this and solve for it, we get Q groundwater equals negative 450 CFS. Okay, or we could say that Q groundwater equals 450 CFS out. Okay, so that's how we solve it. Okay, I will note, this is kind of an interesting problem because at this current moment, what's happening here, and this probably would not happen there, who knows exactly, but this kind of implies something interesting about the behavior of this river at this moment. So I'm going to erase all this, and I'm going to zoom in and kind of talk about this for just 1 second. Okay, so first thing I want to note is that more water is coming into the system via river flow than is leaving. Okay, so we've got like a big arrow here and a smaller arrow here. Okay, so that implies that there was a flood upriver, or rain or whatever, flood or rain upriver. Okay, and that flood is moving downstream. Okay. The other possibility actually that's really the only real possibility here, right? Because then what's happening is as the water is rising, okay, the water is leaving due to groundwater, okay, because the level of the water in the ground is below whatever the equilibrium level should be, okay, so for the river at the height that it's rising to. Okay, so now we've got water leaving. Okay, note that typically, if the water is rising, typically we would expect the opposite to happen. So typically we would expect, if the water is rising in the river, that one of the reasons it's rising is that the groundwater is coming in. Okay? And usually in that case, though, what would end up happening is that you would have more leaving than coming in. Okay? And that would imply a local rainstorm. Okay, so those are kind of two different, those are just two different situations, right? And so, you know, like for example, where we live on the Mississippi River, we almost always are in this situation where our river is kind of controlled by what's going on upstream. I'm sure that it's hard to imagine a case where the local rain really makes a difference. But as you move upstream, you know, if you were to go to the mouth of the Mississippi River, you would get systems that are kind of controlled by the local rain. Okay, so that's just, you know, an interesting thing. Okay. All right, so the next one. It would surprise me if you didn't know this one was coming. This one is easily the most involved one. It's very hard to get the answer correct because there's just so many little things going on. Most of you got the procedure correct. Even if there was an error somewhere along here, there's just kind of a lot of things going on. So this one kind of, you know, points wise, it's hard to get a 10 out of 10 on this one. And that goes for me as well. Who knows, I might make a mistake right now. That's just the way it goes. Okay, so negligible viscous effects or inviscid, that always tells us we can use Bernoulli. Okay, so that means Bernoulli is kind of where they're driving us. They're saying, don't worry about the energy equation. Don't worry about head loss. Don't worry about, well, there's no pumps or turbines, but don't worry about head loss. Okay, so determine the flow rate if the manometer fluid is oil. Okay, so typically what's, you know, so in this case, I'm thinking that in all of these problems, almost always, so we're trying to get at Q, so we're trying to get at V. And Bernoulli is usually our master equation, so we're going to go ahead and I'm going to do it here. I think on the key I did it differently. Okay, with my points being at the bottom of this manometer, because I want to be able to take advantage of the manometer. Okay, so so knowing all of that, the only thing I'm going to do right off the bat is I'm going to rearrange it like this. I'm just going to rearrange it so that I've got P2 minus P1 over gamma. And this is the gamma of the fluid that's in the pipe, which I believe is water. Yes, it's water. So we will make that gamma water. Okay, and plus, I'm gonna put these next to each other as well, because I know that the z's, you know, are going to become important like that. And then, well, I mean, it doesn't really matter. Just because of where I am on the board, let me just go ahead and do it here as well. Okay. So I moved all the points next to all the things next to each other, just because I know that each one of these equations, you know, I know that this one's going to come from the manometer. I don't know how I'm going to deal with that one, but a lot of times it disappears because of the manometer, and I know that this one's going to come out of continuity. Okay, so that's why we're doing it that's why I've kind of put them together like that. Okay, so let's start with the manometer. Okay, so the manometer. Okay, these are our sides, as I usually like to call them. Okay, so the manometer, we're going to start at 1. And that is really bad, but that is not my puppy. That is the dog that my puppy shares the yard with, if you can hear it howling in the back. All right, so we're going to go from, so we start with P1, and we're going to add as we go from up here to here. Okay, so that's going to be plus gamma of water, and we're going to go up Z2 minus Z1, and then I'm going to go up this distance, which is unknown, we'll just call it capital H. It's capital H, and we're going to keep up going through the water, plus H sub M. Okay, so now we're not going to worry about this bit here because we go up and then we come back down. But now we're going back downwards through the fluid. Oh, wait, excuse me. You probably caught that error. Let's, we were going upwards in the fluid, so that should have been a minus sign. Let's make that red just to accentuate my error. Okay, as I said, you know, it's hard to get this one entirely correct. So anyway, so as we're going back downwards through the fluid, so right here, we're going down, gamma of the oil times H sub M. And then we're going to go this bit, H, that capital H, back down, plus gamma of water times, capital H. And that gives us 2P2. Okay? So if we rearrange this manometer equation, so I'm gonna bring the P2 over to the other side, so I'm gonna end up with P2 minus P1, and then, so I'm gonna bring this over there, and then I'm gonna divide both sides by gamma water. Okay, so let's be gamma water. So what I'm gonna get here, gamma water, okay, because I'm trying to match with my Bernoulli equation, equals, let's see here, so the gamma waters cancel, Z2 minus Z1. This H here and this H here are going to have opposite signs, so they're going to go away. Okay, plus H sub M plus gamma oil over gamma water times H sub M. Okay, and that, has a, it has kind of a nice look on it, oh wait, sorry, I apologize. Algebra error. Really struggling today. Okay, we'll put my other error in red here. This is a minus. Okay, because that minus has to, what's the word for it? It's got to distribute through. Okay, so this thing right here, we recognize gamma oil over gamma water. That is S oil. Okay, so that's a specific, that is by definition the specific gravity of oil. H sub M minus H sub M plus Z2 minus Z1. Okay, P2 minus P1 over gamma W. Okay, boom. Okay, so that's basically how I got the solution. And so we'll say P2 minus P1 equals, we're going to leave this as Z2 minus Z1. Note, if that's uncomfortable for you, you can call this, X if you want to. And then note that when you work the Bernoulli equation, you can make Z2 X and Z1 0 if you wanted to. Okay, if that, kind of makes it work out better for you, that's up to you. Okay, so H sub M is 1/2 foot, okay, as given. Okay, and then plus S sub 0, which is 0.88 times that 1/2 foot. And I don't know why I'm using fractions here. It's not really that important. Oh, sorry, over gamma W. Over gamma W. Okay, Z2 minus Z1 minus 0.06 feet. Okay, so fairly simple and ready to be plugged into our Bernoulli equation. Okay, so next we need continuity. Okay, so continuity. Okay, so we're going to use in equals out because there's no accumulation in that between 1 and 2. So rho V1A1 equals rho V2A2. Okay, and these rows go away. So let's not get worked up about them. And we'll say V1 times pi times the diameter 1, D1 squared on 4 equals V2 pi D2 squared on 4. Okay, so the pi and the 4 go away. Oh, sorry, that's, I forgot. I kind of just got on a roll here. This is a lowercase d, or a capital D, and that's a lowercase d, I believe. Yes, this is a capital D squared. This is a lowercase d squared. Okay, so rearranging, we'll get V1 equals V2 times D2, or d squared on d squared. Okay, so noting that little d is 1/2 of big D. Okay, so when we plug those in, we're going to get that V2 equals 4V1. Okay, or really, really you get V1 equals 0.25 V2. Okay, but I prefer not working with fractions. Okay, so now we're ready. We can just plug these two things into Bernoulli and we can solve this. Okay, so I'm going to zoom in over here and we're going to plug those terms in and we're going to say, okay, so we're going to say, let's see, V1 squared minus V2, which is going to be 4V1 squared all over 2G equals, okay, let's make sure we're getting this right. Oh, did I get it right? Hold on. I did not get it exactly right. So let's remember again. Okay, another minor math error. Minus sign, minus sign, minus sign, minus sign. Okay, so I'm gonna have to remember that when we plug in over here. So that means we ended up with negative z1 minus z2, okay, minus h sub m. Sorry, not minus h sub m. I'm really struggling right now. Sorry. Okay, minus 0.06, okay, from up top. Okay, minus 0.06 meters. Okay, plus z2 minus z1. Okay, noting that z2 minus z1 right here and minus z2 minus z whatever. These things are going to cancel. Sorry, geez. 2, 1. Okay. Yeah, 2 and 1, right? Okay. So these are going to cancel. Okay. And then I only have one unknown left, okay, and that's over here. So I'm going to get negative 15v1 squared over 2g equals negative 0.06 meters. Okay, notice the negative signs go away. They have to because we have a square. We're going to end up taking a square root. So there's really no way for this to work out otherwise, okay? So if you get to this point and you don't have a negative, and then, you know, you end up, like algebraically it doesn't work out, you made a mistake. Now, I would understand if you kind of just ignored the negative and moved on, but in your head you should be thinking, okay, if I have time, I've got to come back to this problem, okay? 0.50754 feet per second. Okay, so that's V1. And the question asked for Q, so we'll see Q equals V1A1. And if we plug that in, we'll say Q equals 0.50754 feet per second. Okay, times pi times 4 over 12 feet squared divided by 4. Okay, so the Q equals 0.044291 CFS, cubic feet per second. So Q is 4.43 times 10 to the negative 2 CFS. Okay, so that's where we are. All right, so on to the last one. I will note before I get to the last one, wherever it is, there it is, that this was, so all three of these I expected to be, you know, to test your knowledge, to be solid questions. This was the challenging one. And the reason for that was this, you know, you were supposed to assume the pressure is hydrostatic. And you know how to work with a hydrostatic thing. It's just a force on a gate. But this is kind of out of context, right? And so not a lot of people got this. I think the 4 people who got it, the hydrostatic force is all the way correct. We're also the 4 people with the highest grades in the class, my 4 A's. So just to be aware, this was kind of sneaky, which I don't really like to be sneaky, but I thought with this hint that you would be able to get it. And I would say about, I don't know, maybe half of you figured out how to work with the hydrostatic, but only 4 of you actually got it 100% right. So what, you know, so my thought at first was, I was like, well, I'll curve this test. You know, I'll give you an extra, because I think getting those forces right, or getting those pressures were worth 2 points out of the 10, and then getting the total force was another 2 points from there. So 4 points total to getting those forces. So I think what so I was like, well, maybe I'll just give everybody 2 points. But I think what I'm actually going to do is I will add some points onto the final, okay, to account for this. Okay, so just, you know, there will be a small curve on the final because of this, and I'm not going to forget that, so don't worry. All right, so anyway, we're looking for the y direction force in the Mississippi River banks with the water through the cross-section of downtown New Orleans when the flow rate is 6,000 CFS. This is fairly typical. Okay, this is not a flood or anything like that. These depths are about typical, and the cross sections are approximate. Okay, so I mean, I made up this data, but it's fairly typical. And so, you know, as an order of magnitude, this will kind of, you know, this will kind of give you an idea, which is kind of cool to be able to kind of sit back and think about this problem. One thing that I want to note here is that before I start working this, I don't know what the one thing is I wanted to note. Is that the final answer? So if I did not just in the y direction, which is all I asked for here, because of the time constraints. And notice also I picked a problem that had no gravity because I didn't want to, I was trying to make it easier. But the total answer for this, if we solve it all the way, is that in this bend, with these numbers that I made up, which are fairly typical, was 1.11 times 10 to the 9th pounds, kind of off in this direction. Okay, so that's what the levee and whatever's beneath the levee, that's what it's supporting, which is pretty awesome. I mean, it's just crazy to think about. Okay, the last little bit of this, there's so many of you guys that just forgot this. The pressure terms and the momentum terms. Which one is more important? And all you had to do was look at your answer and tell me which one was bigger. And a lot of you forgot to do it, which was very upsetting for me. Okay, so here's cross section 2. Okay, and it's got kind of like a little angle going on here, 10 degrees. Okay, and here's cross section 1 somewhere over here. Obviously, I don't know exactly where I put. Oh, you know what? I put it to make it exactly horizontal, because I didn't want you to have to deal with an angle on that one. So we're going to make it exactly horizontal. Okay, so this will be cross section 1. All right, so we're going to go ahead and solve this. And so the way we do this is we're going to go in the y direction. The y direction was given as being up, okay, or north-south. Okay, so we're going to go sum of the forces in the y plus the sum of the momentum terms in the y, m dot v y. Okay, those are the ins, equals the sum of m dot v y out. Okay, so the nice thing here is ultimately, I really wish I had a color that showed up on that background a little better. Maybe the red will show up. Is that, okay, so if I do my free body diagram, I've got these velocities. So this is v1, this is v2. So those are going to those we're going to have to account for in the velocity term, right? I mean, in the momentum term. So I've got a momentum term. Are those both in the y direction? This one definitely has a y component. They both have y components. So they're both going to be in our equation. All right, what else are we going to need? Well, we've got forces on this thing, obviously, or else we wouldn't be asking this question. Okay, so one of them is going to be on this free body diagram. Okay, if this is my control volume. Okay, one of the forces is going to be the force of the bend on water in the x. And then we've got the force of the bend on water in the y. Okay, that's cool. Other forces that we have is we're going to have the pressure force here. Okay, force of pressure on 1. And we're going to have the force of pressure on 2. And remember, the pressure forces always push. Okay, force of pressure 2. Okay, so those are all of our forces. So we've got 3 forces in the y direction. And we've got 2 momentum terms. So there's going to be, in the y direction, there's 5 things going on. The x direction is a little easier, but I didn't ask for the x direction. Okay, so, because the x direction, we could ignore everything that's happening at 1, because none of that affects the x direction. All right, so let's see. So some of the forces in the y direction. So the first one is the one we're solving for, which is force bend on water in the y. I'm going to kind of zoom in now. Actually, I don't want to zoom too far in. We still need to be able to see our picture, right? Come on. Okay. Plus. Okay, now we've got to get all of our forces in the y direction. So FP1, okay, which is going straight up, so we don't need any angles on that. The FP2, okay, which is going at an angle, so we need the sine of that 10 degrees. Okay, so those are all the forces in the y direction. And now I need the in velocity. We need to account for this in velocity. So that's going to be m dot, so it's going to be rho q v1 equals the out, which is going to be rho q m dot. And then the vy right there, notice it has a negative vy, so it's going to be negative v2 sine of 10 degrees. Okay? And so that's really, this is the whole setup right here. That's the whole problem, really. Whole problem. Okay? All you have to do is plug in right, okay? Okay, just plug correctly, which is not easy at all. I don't want to pretend that it is. Okay, but once you're here, you know, you've got most of the work done. Okay, so we're going to look at the things that we don't know. So first, let's look at these pressures right here. So I'm going to go over here, and I'm going to do FP1. Okay, so normally the way we've been doing this, we've been saying, okay, well, we just take the pressure and we multiply times the area, right? And I said it's hydrostatic. Well, that means that the pressure at the surface is 0, but the pressure at the depth is not 0. So if I were to draw this face, you know, it looks, you know, let's suppose it's rectangular like this, okay? And this would be Woldenberg Park, and this would be Algiers Point. And, you know, the river is flowing through this, kind of actually to the north, right? Well, right up here, the velocity is 0, but at the bed, the velocity is really high because it's deep, right? So it's got a, you know, pressure prism, okay? And, you know, I don't know how to draw that for this whole thing, but, you know, you got the idea, right? So remember, how do we deal with pressure prisms? Well, we want the average pressure and multiply it by the whole area. So we'll do the average pressure and we'll multiply it times the whole area. Okay, well, how do we get the average pressure? Well, you can think about it as the centroid, or because it's a rectangular face, you just think it's, you know, halfway down. It's going to get your average place. So it's going to be gamma times h bar times a. So gamma, h bar in this case, well, this face is, let's see here. So it's, for P1, it's 120 feet deep. So this is going to be 120 feet divided by 2. And then our area is going to be 120 feet times 6. How wide is this? 180 feet, I think. Yeah. Right. So if we solve for FP1, okay, we get 8.0870 times 10 to the 8th. Okay, pounds. Okay, that's ridiculous. Okay, utterly ridiculously large number. Okay, and I think hopefully with this, you know, one of the points here was hopefully to get you to see one of the values of scientific notation, which is, like in this problem, you can easily compare terms to see which ones really matter. Okay, so we'll do FP2, and it works the same way. So I'm just going to pause it and have it kind of pop up. All right, so we end up with 6.24 times 10 to the 8th pounds. Okay, so that's, you know, that's the pressure at 2. Now, 2 is on an angle, so, you know, so not all of that is going, you know, north-south. Most of it is going east-west. So it's not really going to affect that bank all that much. Okay, so let's, or at least not in the y direction. Okay, so let's see. So let's go look over here. So we've got those two pressures. What else do we need? We kind of got a road. We have a Q. Q is given. So we need these velocities. Okay, so this velocity and this velocity. Okay, and then we'll be ready to go. Okay, so that's going to be a little continuity for us. So let's go down here and let's do some continuity. We have a flow rate going through a rectangle. A lot of you decided to use pi d squared on 4. I don't really understand why you would use pi d squared on 4 on a rectangle. It's a rectangular cross section. The area is the depth times the width. Okay, so for example, Q equals VA. So V equals Q divided by A. So V, then in this case, so for V1 is 600,000 CFS. And we're going to divide that by the area, which is 1,800 feet times 1,200 feet. Okay, so that's how you get V1, which ends up being an annoying 2.7778 feet per second. Okay, and then I'm just going to do the second one. Okay, and so there's the second one. All right, so that means if we go back up to this original equation up here, if I plug all those numbers in, this sucker is just gonna fall out of our lap, and it's gonna be, you know, it's gonna give us an answer. Okay, so I'm gonna do that. It's not really a whole lot for me to say while I'm doing it. I guess I could just, you know, do it F Bowie, okay, plus FP1 8.08 times 10 to the 8th pounds plus 6.24 times 10 to the 8th pounds. Okay, so those are our pressure terms. And this one's going to be multiplied by the sine of 10. Okay, that's going to make it significantly smaller. Plus, and this is our first momentum term. Okay, so the rho of water, and this continues to be a problem of people not getting the correct rho, but rho is going to be, I guess I'll do it down here, 1.94 slugs per cubic foot, okay, times the flow rate, Q, 600,000, CFS, times 2.7778 feet per second, okay, equals, I like having my momentum terms underneath each other because they look so similar, okay, times 600,000, okay, times 3, that's a dot, feet per second, times the sine of 10 degrees, okay, noting that this has a negative sign right there, okay. So if we, if I kind of draw this all out just to kind of give you an idea of what this looks like, 8.08 times 10 to the 8th, okay, pounds, plus 1.0836 times 10 to the 8th pounds. Okay, those are order 10 to the 8th, plus 3.2334 times 10 to the 6th pounds. Okay, a big number, but 100 times smaller than my pressure terms, equals, okay, negative 6.0638 times 10 to the 6th pounds. Okay, so notice that if we solve all of that, and the number is not terribly important, but end up with a negative 9.2090 times 10 to the 8th pounds, or F Bowie equals 9.21 times 10 to the 8th pounds to the south. Okay. Now, notice that order of magnitude is not even close. These 8s means 100 times bigger than these 6s. Okay, so the pressure terms clearly are dominant. So much so that really, you can look at it, and if we just added these two up, you basically get this. We could almost ignore this. Okay, and that's pretty crazy. Now you might say, okay, but this was like typical situation. And what I really liked is that a lot of you guys used your intuition, and you said, my intuition says it's going to be the momentum, so you just wrote that it was the momentum. But I really wish you had looked at the numbers that you got. Some of you wrote down momentum without looking at your numbers. This was all in your numbers. All you had to do was look at them. But what's really cool about this is really surprising. It's surprising to me too, because you would think with all this water having to be turned, but this is a really, really deep river. Okay, and so the pressure terms are more important in this case. And you will read some, like if you read there's a book called Rising Tide, and it's all about the 1927 flood in the Mississippi River. Highly recommend you read it. It's really interesting because there's a lot of engineering in there, and river engineering, but also more importantly, it's really about society and class and race, and it's really kind of amazing and kind of a horrible story in a lot of ways. Ultimately, there was the big flood in the Mississippi River in 1927. And I'll give you the punchline, but the punchline comes in the middle of the thing, was everybody all up and down all the rivers that fed into the Mississippi were scared of floods. And in New Orleans, they ended up dynamiting the levee downriver in Plaquemines because New Orleans was richer than Plaquemines. They had more money. And in order to do that, they guaranteed the people in Plaquemine that they would pay for whatever their losses were. And the people in Plaquemine decided not to fight because what choice did they have? And then, and then it plays out from there. But they dynamite the river in order to create a spillway. Now we have the Bonnie Carey, we have the Morganza, we have a couple of spillways. Not saying those are perfect, but But one of the things when you read a book like this is the guy who writes it, he's a historian. He's not an engineer, and he talks all the time about, the strain on the levees, during this flood. And he's always talking about he talks about the pressure, but really he keeps talking about, the levees have to turn the river. They have to deal with that momentum, this mountain of water hitting the levees. And it is true, the momentum terms do create large forces, and we can see them right here. But it's the pressure that matters. Okay. Now keep in mind that in a big flood, we could redo this problem, and what's going to happen is during a big flood, the river might get, I don't know how much deeper it gets downtown New Orleans, but maybe it gets 10 feet deeper in downtown New Orleans. Let's just imagine if it gets 10 feet deeper. So these numbers go from the depth of 100 feet to 110 feet, and the other one goes from a depth of 120 feet to 130 feet or something along those lines. But in the meantime, the velocities might double. Okay, and if the velocities double, then these terms, okay, because ultimately they have a v squared in there, because they have a v and a q. So they have a v squared in there. And so these are going to increase faster than these, okay, in a flood. I still don't know if they're going to be of the same order. We could do that math. The last thing is to note is that some of you guys try to do Bernoulli here. Bernoulli is not going to work for you for a lot of reasons, but one of them, the most obvious one, is I pick a point here, 1 and 2. If I'm on the surface, well, here's my streamline. I have no pressures. The elevations are the same. The velocities are different, okay? And that's a little bit confusing, right? So if we think about Bernoulli, okay, so the pressures are 0, the Zs are the same, and these are different. So how did that work? Well, it works because there's all kinds of forces between 1 and 2, okay? So you can't say that this is inviscid. There are forces acting on this thing between 1 and 2. Okay, so there's a lot of viscosity going on here. There's normal forces on the sides, okay? Even if these were the same, this equation would yield you nothing, right? It would just be a bunch of zeros, and you'd be like, okay, well, it's not helpful. Okay, so what if I go at depth? Well, if you go at depth, well, then the pressures will be, let's suppose you go down, 50 feet. Well, now they've got this, hydrostatic pressure, so the pressures are the same on both sides, right? The Zs are the same, okay, and you end up with the same problem. So Bernoulli is just really not helpful here. Yeah. And when I talk about all these viscosities and these normal forces, all of those get combined into what we call the force of the bend on the water. Okay, so that's it. Hope this helped. Let me know if you need anything else. All right, hope all's well. Bye. Whoa.